Martinez, and this is Group 1 on Lab 8. In this lab report, we'll be focusing on one of the most important ideas in physics: how momentum and kinetic energy behave during collisions. Momentum, which is mass in motion, is conserved in every collision as long as no external forces interfere. That means the total momentum before two objects collide is exactly the same as the total momentum after the collision. Kinetic energy, however, doesn't always behave the same way, and that difference is what we will be experimenting with today. In physics lecture, collisions are generally classified as either inelastic or elastic. In inelastic collision, objects bounce off each other without permanent deformation or without generating any heat. Because of that, both momentum and kinetic energy are conserved. This is the idealized type of collision often discussed in textbooks and modeled in controlled environments. In contrast, an inelastic collision involves deformation, heat, and/or objects sticking together. In these cases, momentum is still conserved, but kinetic energy decreases because some of it transforms into other types of energy, such as sound or thermal energy. Researchers use these distinctions to understand everything from particle interactions to high-scale impacts. In this lab, we'll observe the momentum and kinetic energy change during different types of collisions using our track and carts. By comparing the motion before and after impacts, we can see conservation of momentum in action and measure how much kinetic energy is lost or preserved depending on the collision type. These principles show up everywhere in real life. Car safety engineering, for example, relies heavily on understanding inelastic collisions. Crumple zones are designed to absorb kinetic energy by deforming, which reduces the force on passengers. Even high contact sports such as football depends on the same physics that we are studying in this lab report. By analyzing these types of collisions in a controlled environment, we gain insight on how energy and momentum influence the motion of objects all around us. Now I'll be passing it to Daniela, where she will then explain all the materials that we used in this lab and how we use these materials to conduct our observations.
Hi, my name is Daniela Avila, and now I will talk about the materials we used for the lab number 8. For this experiment, we used several materials to study collisions and analyze how momentum and kinetic energy change before and after the interaction. First, we used a track with carts. These carts allowed us to simulate collisions in a controlled environment where the objects could move in a straight line with minimal friction. We also used two carts with different masses. In some cases, the carts had the same mass, and in other cases, they had different masses. This helped us to compare how mass affects momentum and energy during both elastic and inelastic collisions. Additionally, we used cars that already had built-in magnets and other attachments. The magnets were included in the carts, which allowed us to create elastic collisions where the carts bounce off each other without touching. For inelastic collisions, we adjusted the carts so they will stick together after the collision. We made sure to measure the mass of each cart before starting the experiment. To do this, we used a double balance scale where we placed the car on one side and other weights on the other side until both sides were equal. This was important because accurate mass values help us calculate momentum and kinetic energy more precisely. To collect our data, we used sensors connected to the capstone program. These sensors recorded the velocity of the cars before and after the collision, allowing us to calculate momentum and kinetic energy. We also used a computer to run the capstone software and analyze the data we collected during the experiment. All of these materials were essential because they allowed us to observe different types of collisions and measure motion accurately. Now, I will pass it to my teammate to explain the procedure.
My name is David Maldonado. I'll be in charge of procedures for lab number 8. For the objective, we will be observing how the momentum and kinetic energy are affected by a collision. For objects that are not rotating by momentum, we mean mass in motion. When two objects collide, the total momentum is the same before and after the collision. Kinetic energy is another story. Net momentum before the collision equals net momentum after the collision. We will call elastic collision where the colliding objects rebound without lasting deformation or generating heat. We will call a collision inelastic when the colliding objects deform, produce heat, or even stay stuck after the collision. We'll be placing magnets in the car. We'll figure out how to place the magnets in the cards or the magnets to produce the closest to a perfect elastic collision possible and the inelastic collision possible. We'll change the sign to one of the cards, allowing us to see our velocities with the same sign for the table as a frame of reference. We'll weigh both cards to discuss with our teammates or with each other if we are going to use our velocity graphs, or we can use momentum and kinetic graphs to set capstone properly. We'll use momentum equals mass times velocity, and kinetic energy equals half mass times velocity to the second power. For data, we'll collect our momentum and kinetic energy just before and after the collision in 4 following cases: inelastic collision with 2 objects with the same mass, elastic collision with 2 objects with different masses, inelastic collision with 2 objects with the same mass, inelastic collision with 2 objects with different masses. We'll be using table 1, which is same weight, different weight. The two cards, which is blue and red in the total. Elastic collision before and after, inelastic collision before and after. After that, we'll calculate the percent difference in total momentum before and after the collision and the kinetic energy for each of the 4 cases we're working with. This will be table 2, percent difference of values for momentum and kinetic energy before and after collision. We will then produce a relative perfect elastic collision between the 2 cards. How do we produce a relative perfect inelastic collision between the 2 cards? Were there other options to achieve your proposals to produce a relatively perfect collision? When we say something is conserved, the perfect difference is near or far from 0. Why? The theory says the momentum is conserved in both cases. Does your data support the argument? Why or not? What do you think affects your experiments? In which case can you say the kinetic energy is conserved and in which not? What criteria are you using to determine the conversion or the conservation of each quantity? We'll then write our lab report, passing it off to my next group member.
Is Alejandro for data and data analysis on Lab 8. For Lab 8, our first part was to get the weights of our cars. We had a red and a blue car. For our red car, our mass came out to 271 grams, which converted to 0.271 kilograms. Our blue car was 270 grams, which converted to 0.270 kilograms. The first important part of the lab was the elastic momentum, which is P equals mass times velocity in kilograms per meter squared. We measured a before and an after for our momentum. For our before, we plug in PB equals 0.16 plus negative 0.18, which gives us a momentum before the crash of negative 0.02 kilograms per meter squared. For our after, we got PA equals M1 V1 initial plus M2 V2 initial, which is PB negative 0.14 plus 0.11, which gives us an after momentum of negative 0.03 kilograms per meter second. Using our momentum from before and after the crash, we can plug in the absolute value of negative 0.03 minus negative 0.02 divided by 0.02 times 100, which gives us a 50% difference. Our next part is elastic kinetic energy, which we use the formula K equals 1 over 2 times mass times velocity squared. For our before, we got KB equals 1 over 2 times 0.05 to the power of 2 plus 1 over 2 times 0.06 to the power of 2, which gives us a kinetic energy before the crash of 0.00305 joules. For after the crash, we get the formula 1 over 2 times 0.04 to the power of 2 plus 0.02 to the power of 2, which gives us a kinetic energy of 0.01 joules. Plugging in our before and after crash kinetic energy to the percent difference equation gives us absolute value of 0.001 minus 0.00305 divided by 0.00305 times 100, which gives us a percent difference of 67.2%. For the next step, we flip the cars into the sticky side in order to get an inelastic collision where the two cars collide and join together after the crash. For before, we use a formula PB equals negative 0.19 plus 0.17, which gives us a momentum before the crash of negative 0.02 kilograms per meters per second. For after the crash, we use a formula PA equals m1 plus m2 times final velocity, which gives us a final velocity of negative 0.01 kilograms meters per second. Using those two numbers, we get our percent difference formula. Absolute value of negative 0.01 minus negative 0.02 divided by negative 0.02 times 100, which gives you a percent difference of 50%. For inelastic kinetic energy, we use the formula P equals 1 over 2 mass times velocity squared in joules. For before, we get KB equals 1 over 2 times 0.05 plus 0.07, which gives us a kinetic energy of 0.095 joules. For after the crash, we get KE equals 1 over 2 times 3.96 times 10 to the power of negative 4, which gives us a kinetic energy after the crash of 1.98 times 10 to the power of negative 4. Using those numbers, we plug it into our percent difference equation, which gives us the absolute value of 1.98 times 10 to the power of negative 4 minus 0.095 divided by 0.095 times 100, which gives us a percent difference of 99.8%. We weren't able to do the second part of the lab because our program wasn't working, where we changed the mass of one of the cars.
To conclude our video, the software was not giving us enough accurate data for us to calculate correctly. The blue car was not functioning correctly, then after a quick reset of the program, the red car wasn't working. The software on our computer was not functioning properly how it was supposed to, and after multiple attempts of trying to fix it with the help of our TA, we ended up having to change our computer around the end of lecture. Unfortunately, that only gave us time to do the first section of the lab and not the second part, where we would have had to put a weight on one of the cars. Thankfully, our TA informed us that we would still receive full credit.